Newton's third law. All right, so once again, to summarize, Newton's third law is basically the one that says for every action there is an equal and opposite reaction, but that's a bit of an oversimplification. It's more true to say that when a force acts from object A to object B, there will be an equal size but oppositely directed force acting from object B back on object A. It's always pairwise and it's always between two different objects. So if you think about what's going on, if we have an object A and an object B, and they undergo some kind of collision. So they were originally traveling towards each other, and they strike one another. At the moment they strike one another, there will be a force due to B acting on A in one direction, and an equal sized but oppositely directed force due to A acting on B in the other direction. So each object experiences a force, but those forces are in opposite directions. The third law is problematic. We as human beings, we're pretty sensitive to accelerations. We do have some built-in accelerometers that are pretty sensitive. And I think that we have a tendency to think in terms of acceleration. So let me ask a closely related question. If you have an, I should label the objects too. Let me do that. This was object A, this was object B. If we now have a much smaller object A colliding with a much bigger object B, then what can you say about the forces? And the temptation is always to say that, well, the force on A must be bigger. Obviously, it moves more, it changes its motion more, it accelerates so much. And in fact, that is incorrect. It will be true that the forces on each object will still be the same. And you may be thinking, how can that make any sense? The accelerations are obviously different. You're right, the accelerations are obviously different, but we're basically saying the magnitude of the force due to B on A is equal to the magnitude of the force due to A on B. And if we think about what F equals ma, Newton's second law, has to say, that means we expect the mass of A times the acceleration of A to be equal to the mass of B times the acceleration of B. If these two things are to be equal to each other, with ma being less than mb, then the only way that that can happen is if the acceleration of A is greater than the acceleration of B. So, in fact, Newton's second law does tell us if the forces are equal between two objects like a less massive A and a more massive B, then we do in fact expect object A will accelerate much more than object B. Now, the way this usually shows up in sort of conceptual questions is asking something like, imagine a UPS truck gets in an accident with a smart car. Smart cars are tiny, UPS vans are huge. Which one is going to experience the larger force? And there's always that temptation to go with, well, the smart car accelerates more, clearly it's the smart car. But no, it has to be the same. In fact, it's down to a symmetry of the universe that it has to be the same. If two objects collided with each other but one experienced a much larger force than the other, you could do these weird, almost reactionless rockets if you wanted to. Basically, everything that we know would work really, really differently. The universe would look unrecognizable. So this is a necessary condition for the universe as we observe it. So yeah, it's going to be a thing. Whenever two objects interact, whether one's large and one's small, you'll always get equal forces on the objects when they touch. There's even equal forces acting gravitationally. You're being pulled down by the Earth. Well, that means gravitationally, you're pulling up on the Earth. There's got to be a Newton's third law pair there. Okay. This idea explains a lot of interesting phenomenon around us. For instance, consider when you have a cannon and a cannonball. You have the cannon, you set off the gunpowder, there's this huge force acting on things internally to the barrel, and in the end, we get the cannon recoiling a little bit, and the cannonball taking off to the side at a high speed. And how can we understand that? Well, basically, we can understand it as the force on the ball must be equal in size to the force on the cannon. But the mass of the cannon is greater than the mass of the ball. So that means the acceleration of the cannon must be significantly less than the acceleration of the ball, which is why, for the short period that they're in contact through the explosive force inside, you get the cannonball accelerated a lot and moving fast, and the cannon accelerated little and rolling backward relatively slowly. The same thing really happens with something like a gun. You're holding the gun, you're adding your mass to it, it's already heavier than the bullet. You fire the gun, it ends up accelerating the bullet much more than it accelerates the gun, even though the forces are equal. So the majority of the kinetic energy ends up in the bullet instead of in the gun. We'll talk more about that when we actually talk kinetic energy, because it's interesting to see how that works, because it's a whole other thing. Alright. Trying to think if there's anything else I want to say with this. Mostly, I think this is it. You do have to be super careful with Newton's third law. The first and the second are pretty tightly related. The third, it's the hard one to understand. You need to remember the sum of forces equals ma, and you have to remember the third law. In fact, when you're looking at a problem, you should be thinking about, are those two forces a third law pair? Most of the time the answer is no, they have to act on separate objects. And the other thing you should be thinking about is, well, if there are two objects interacting, they experience equal-sized forces, period, due to that interaction. Two things hit each other, well, they experience the same size force during the entire collision. It can't be different. It has to be the same, and you can remember that by remembering Newton's third law and forcing yourself to think about it. Because otherwise your instincts with accelerations will take over, and you'll tend to say that whichever one experiences the larger acceleration experiences the larger force, and that's not really the case. Alright, we're going to stop there, so I'll see you in the next video.